So let me ask you a question. How fast are you moving right now? I mean, right this second. The answer, believe it or not, is way more interesting than you might think. Today, we're going to dive into relative motion. And it's one of those ideas in physics that just completely changes how you see the world, from a car driving past you to the stars in the sky. And the best part? It's all built on one super simple concept.
All right, let's kick things off with this little puzzle. As you're sitting there watching this, are you moving? Go ahead, what's your gut answer? Yes or no?
Okay, so here's the thing. If you said no, you're absolutely right, from one point of view. But if you said yes, guess what? You're also right. The answer completely 100% depends on your point of view. And that little idea, that's the key to everything else we're going to talk about.
Let's just break that down for a second. Think about it. Relative to the chair you're sitting in, you're not moving at all. Makes sense. But let's zoom out. Relative to the center of the Earth, you're on a giant rock that's spinning at over 1,000 kilometers an hour. And if we zoom out even more, relative to the sun, all of us are hurtling through space at a staggering 107,000 kilometers per hour. So you see, talking about motion is pointless unless you first answer the question, relative to what?
So, that point of view we keep talking about? Well, in physics, it has a proper name. And it's the most important idea for understanding all of this. It's called the frame of reference. To really get this, let's picture a classic physics thought experiment. You're on a train. It's moving super smoothly, at a nice, constant speed. You're holding a ball, and you just drop it. What do you see? What path does that ball take?
Well, from your perspective on the train, from your frame of reference, it's totally normal. The ball just falls straight down and lands at your feet. Exactly what you'd expect if you were just standing still in your house. Seems obvious, right?
But what if you're not on the train? What if you're standing on the ground watching that train zip by? You would see something completely different. You'd see the ball fall, sure, but you'd also see it continuing to move forward at the same speed as the train. It would trace this perfect arc through the air. It's the same event, but seen from two different viewpoints, it looks like two completely different things happened. And this brings us right back to our key idea, the frame of reference. It's really just a fancy way of saying the viewpoint of the observer. The person on the train has one frame of reference, the person on the ground has another. And here's the crucial part, neither one is more correct than the other. They're just different.
You know, Physics Libre text puts it perfectly here. Motion doesn't just happen in a vacuum. You have to say what your reference frame is. Without it, saying I'm going 100 kilometers an hour is basically meaningless. 100 kilometers an hour relative to what? The road? The car next to you? The sun? It all matters.
Okay, so now that we've got that core idea down, let's apply it to stuff we all see every day. We'll start simple, with things just moving in a straight line, in one dimension. We've all felt this driving on a highway, right? When a car passes you going the same way, it almost seems to just drift by slowly. That's because your brain is intuitively calculating the difference in your speeds. But a car coming towards you in the opposite lane, whoosh, it feels insanely fast, and that's because you're adding your speeds together. So let's put some actual numbers on this. Picture a motorcycle absolutely flying down the road at 120 kilometers an hour. It's about to pass a car that's doing a steady 90. From the driver's seat of that car, how fast does it look like that motorcycle is going? Yup, they're going in the same direction. So you just subtract. 120 minus 90 gives you 30. From the car's frame of reference, that speedy motorcycle is just pulling away at a pretty chill 30 kilometers an hour. What a huge difference compared to its speed relative to the road. All right, so straight lines are pretty straightforward. But what happens when things get, a little messier? What if motion isn't just forwards and backwards, but can be sideways too? This is where we get into two dimensions. And what's really cool is that the fundamental rule doesn't change. We just add the motions together. The only catch is that now our motion has both a speed and a direction. So in physics, we draw them as arrows, which we call vectors. The final, actual path of an object is just what you get when you add all those arrows together.
Okay, check this out. This is a real problem pilots deal with all the time. The pilot wants to fly straight north, but there's a problem. A strong wind is blowing from the side, trying to push the plane off course. So the plane's actual path over the ground is going to be a combination of where the engines are pushing it and where the wind is pushing it. So what does the pilot do? Well, they can't just point the nose of the plane north. As you can see in the solution, they actually have to aim the plane a little bit into the wind. They point it slightly northeast to let that crosswind push them back onto the correct path. It's a perfect real-world example of adding two different motions, two vectors, together.
All right, we've talked about people in chairs, balls on trains, cars on highways, and planes in the sky. So what's the one simple, powerful idea that connects all of this? Let's boil it all down.
So if you take anything away from this, let it be these key points. First, all motion is relative. There's no such thing as absolute speed. That means you always have to ask, relative to what? That question defines your frame of reference. After that, the math is pretty easy. For things in a straight line, you just add or subtract, and for more complex 2D motion, you just add the vectors together to see where you'll actually end up.
And all of this leaves us with one last, kind of mind-bending question to chew on. If every object's motion is just measured relative to some other object that is also moving, is there anything, anywhere in the entire universe, that we can say is truly, absolutely standing still? Something to think about. Thanks so much for watching.